let's further examine the counting vectorizer. In this counting process, we understand that we've got to identify all the words in our corpus, all the unique words, those are the ones we're going to count, and we go about during the counting process. Now, do you think that's going to be relatively slow or fast? What do you guys think? What are your impressions of this counting process? Generally speaking, it's going to be a bit slow. So because it's going to be a bit slow, we have to think about, are there certain ways we can go ahead and do to speed up the process? So one technique we can speed up the process is, can we parallelize the counting process? Initially, this might seem no problem, right? Essentially, we're counting words. Why can't we just take our corpus, take our documents, and split it up? We pass one half to one worker, another half to another worker, or maybe we have more workers. We can go ahead and divvy up the tasks. Say, here you go. Go ahead and count the words. Go ahead and count the words. But when we start analyzing this, there's going to be a problem. And the reason why is because if we parallelize this process, one worker is going to derive a different mapping between column and word. In other words, one worker might identify or might specify that the word programming is going to refer to column 5. And another worker is going to perhaps identify that the word programming is column 200. Another one might say 17 and whatnot. So these different workers might come up with different mappings between column and word. So because of that, it's going to be very difficult to parallelize this process because there's an arbitrary order for the columns and the words, that mapping. So let's talk about a different approach, a modification to this counting process. Ideally, it'd be convenient that every word corresponds to a unique column number. Because if this is the case, that let's say programming is always going to refer to column 200, then we can easily parallelize the process. Additionally, we don't have to figure out the mapping between word and column. So the problem with count vectorizers is that it has state. In other words, it's going to retain information of previous interactions and usage. So we can go ahead and modify the count vectorizer and use a hash function. Let's use a hash function to convert words into numbers. And the thing about the hash function is that a hash function is going to convert inputs into a deterministic value. If we use the same hash function, no matter what, every time we hash a word, let's say apple, it will always return the same hash value. It's deterministic. So let's explore this concept of hashes. In fact, a Python dictionary uses a hash function. It's a hash table. So here let's hash words like hi, Python, and Python and hi. Notice there's some subtleties here. Here Python is lowercase. Here Python starts with a capital letter, capital P. We're going to hash hi, exclamation mark, and hi again. And we notice that if we just change this single word, in other words, you just make it uppercase as opposed to lowercase, the hash value dramatically changes. And we also notice the deterministic property of this hash function. In other words, we hash hi with an exclamation mark, we hash it again, that same string, and we get the same value. So this idea of a deterministic output. If we give it the same input, it will always return the same output. This is desired in our hash function. And the reason why we want this deterministic property is we want to go ahead and use a hash function to go ahead and always gives us the consistent column number for a word. So in other words, if we hash the word Python, we'll always return this value here. And we can take this value, we can do another step to it, and generate a column number, a column index for this word. So another thing that we want a property of regarding hash functions is that ideally we don't want two different words or two different objects to return the same output. Unfortunately, this is an ideality. In real situations, different inputs can return the same output. In other words, we can go and hash two different words and we might get the same hash value out. This is going to refer to a collision, a hash collision. We won't be too worried about that, but that might happen. So by using a hash function, we're going to convert our count vectorizer into what's called a hashing vectorizer. And by using this hash function, it's going to generate this transformer to be stateless. Stateless just means that there is no state to this function. There is no state to this process. In other words, it's not going to retain any information of any other interactions, any usage to them. There is no state. It carries no state to it. In this stateless process will allow us to easily parallelize the counting process. As I mentioned before, using a hash function, we might have hashing collisions. Although in practice, this is inconsequential. So yes, it might happen, but I wouldn't lose sleep over it. And because our transformer is now stateless, there is no longer mapping between word to feature index. Remember that get features names method we use for the count vectorizer that returned us a list that we use to figure out what column refers to what word. We no longer have this because this is a state. This is a state of that count vectorizer. We're not going to have that option when we're working with the hashing vectorizer. So a downside with using the hashing vectorizer is that we cannot look at the results of the hashing vectorizer. In other words, look at the output it gives us when we use a transform method, take that count matrix and say, okay, what word correspond to column 200? I can't be able to do that because I don't have that mapping. I don't have any state to this transformer. Okay, let's go ahead and use the hashing vectorizer in scikit-learn. So we're going to create a object of the vectorizer. We're going to set this keyword argument norm equals to none because by default the hashing vectorizer will normalize the counts. In other words, it will divide each row by, I believe, the sum of square of the counts. If you don't want to apply that normalization, we'll just say norm equals to none. So it's going to return the raw counts, that same output that we saw with the counting vectorizer. Let's go and fit our documents. Let's go ahead and transform them. And there is our output right there. So let's examine here. So we see that our feature matrix has over 1 million columns. That's what we see here. Our feature matrix has over 1 million columns. And this is in contrast to what we saw with the counting vectorizer. In counting vectorizer, we had, I believe, around over 2,000 columns, 2,000 distinct words. And this discrepancy here is that the hashing vectorizer by default is going to use 2 to the 20th power different hash values to construct our count matrix. Although the vast majority of these indices will have no counts across the documents. But this is perfectly fine. We can go ahead and, there is no problem here if we have a large feature space, if a lot of those are nothing but zeros, because we're going to store the output of this transformer, we're going to store this output matrix as a sparse matrix. So there is no hit to us in terms of memory usage. So a lot of empty features, no problem, because they're storing it as a sparse matrix. Let's convince ourselves that using the hashing vectorizer will be faster than the count vectorizer. So import the time. Let's go ahead and start the stopwatch here, so to speak. Figure out the elapsed time and print it out and see what happens. That was pretty quick. So we see the hashing vectorizer is a lot faster. So to recap, we can speed up this counting process by using a hash function. And the whole point here with the hash function is that we want a deterministic output for each of our words. So we're going to construct a hash table In this way, we can easily parallelize a process. So every time we hash the word Python, we get the same output. And given that we get the same output, if we use the same hash function, then we can take that output from the hash function and use that to generate what should be the corresponding column for our count matrix. But, as I said before, since a hashing vectorizer is stateless, it has no state, it doesn't carry a state with it, we cannot do the inversion process. In other words, we cannot inspect and say, okay, what was column 500? What word did that correspond to? We don't have that option with hashing vectorizer. So here we're sacrificing some of that capability for a faster process. Another advantage of having no state is that we can use the hashing vectorizer for online learning. Here comes a stream of words, and there is no state we have to carry, there's no state we have to update for new observations that we see.